Hello everybody. So this week's lecture we're going to talk about the California fire climate and how climate has an effect on basically not only kind of what we see outside in terms of vegetation in California, but just kind of things that we maybe take for granted or kind of are used to at this point in time. So there's a quote at the beginning of the chapter that says, "I've lived in good climate and it bores the hell out of me. I like weather rather than climate." And that's a quote from John Steinbeck. And I think that the important part, at least for me to take from that, is the idea of weather being a challenge and weather being something that changes often and changes frequently, something you're unsure of, whereas climate is something that we should be much more sure of, something that is long-term, something that we understand, and something that we can really see in terms of patterns. And so let's talk about climate for a bit. So I'm going to move myself over real quick. There we go. Okay, so in terms of California's climate, so when we're talking about climate just in general, we're talking about the average and predictable weather properties over long time scales. And so when we say weather properties, what are we talking about? We're talking about things like mean precipitation, not just how much did it rain yesterday, but how much has it rained this month, or how much has it rained in July for the last 10 years or 20 years or 30 years, in terms of the idea of the annual cycles of temperature. So when we say, oh, well, it's going to be August and in September, and we know how hot it gets then. Why do we know that? How do we know that? That's climate. When we talk about water loss by evaporation, evapotranspiration, and runoff, the amounts that we expect and how that affects the fuel moisture, and then how that starts to affect the fire danger. Phenology, the desiccation of vegetation, the idea that we know that the types of vegetation, and then the idea of when it dries out and when it becomes available for fire, the ignition patterns from thunderstorms, all those things play into this idea of climate. And for California specifically, we know it's a Mediterranean climate. So it's the idea of winter precipitation, summer drought, or at least just no big precipitation events throughout the summer, and then you end up with milder temperatures in most areas. So in just trying to discuss the idea of weather versus climate, this would be a good point to pause this right now, because there's a YouTube video up here which I think does a great job of explaining this idea of weather versus climate. But for me, in terms of weather versus climate, what we're really talking about is the difference between short-term and long-term. So weather is the conditions you get in terms of the atmosphere, in terms of the short-term, can change within minutes or hours, days even, whereas climate is how the atmosphere behaves over a long period of space and time. So it's average regional weather patterns over decades or longer. So the example here, it shows Saturday it was raining with thunderstorms, Sunday it's nice and sunny. Whereas here we're talking about the 30-year normal average temperature, and here's all the different months for that 30-year span and what the average temperature looks like. And when we're talking about fire, specifically in fire ecology, the behavior of any given fire that's happening at that time is going to be dependent on the weather. Whereas the wildfire risk, the idea of how we decide, is this fire season, or are these the conditions that are really conducive to fire, those are going to be based on climatic patterns. So we're going to understand our wildfire risk and kind of get our thoughts on what we can kind of do with wildfire or try and see the patterns in wildfire by using climate. Whereas if we're talking about weather, we're really going to be talking about the specific fire behavior that's happening if we have a fire happening at that same time. Slide myself up here, hanging out in the sky. Okay, so with our California climate, there are a lot of varieties in California climates, which then leads to a large diversity of vegetation, associated fire regime, and fire weather conditions. Because if you think about California, the whole reason of having to separate California into those 9 bioregions is because it's such a large area, you can't really just nail it down and just say, well, it has a Mediterranean climate. Tell the people who live in Palm Springs that they live in a Mediterranean climate, or tell the people who live up in Eureka or Arcata on the north coast that they live in a Mediterranean climate, or tell the people who live out in Susanville out by Mount Lassen that they live in a Mediterranean climate, or Lake Tahoe, right? It doesn't really feel that way all the time, but that's something we could say in general for all of California. But really the whole point of, at the beginning, us talking about separating those regions, the North Coast, the Central Valley, the South Coast, the Southeastern Deserts, Sierra Nevadas, is because there is a diversity in the climates that we'll see in those areas. And that's why we see such a large diversity in vegetation. That's why California is such a cool and interesting place to live and be a part of, because I can live here in the Central Valley in Bakersfield. I can drive 45 minutes and be in Chaparral. I can drive another, 30 minutes beyond that and be in conifer ecosystem, and could be sunny down in the Chaparral. It could be snowing in the pine trees and the firs and all of that. I could be in Bakersfield. I could go 2 hours the other way, and I could be up in the Sierra Nevadas and looking at giant sequoia trees. I can drive 3 hours or actually drive another 2 hours in a different direction and be in the desert, looking at nothing but, wondering where the next tree could be. And I could drive 2 hours and I could be at the ocean. So because of that, you're going to have this large diversity of vegetation. You're going to have different fire regimes and different fire ecology, and you're definitely, depending on where if you get a fire and where your fire is, going to have different fire weather conditions to deal with for those different areas. In terms of a Mediterranean climate, that results from differences from seasonal changes in the global circulation of the winds throughout the globe. And so when I say the winds, what we're really focusing on is the location of California relative to the jet stream. So the jet stream is a narrow variable band of very strong, predominantly westerly air currents encircling the globe several miles above the earth. And this is another good time to pause, and you got this link right here to a video that will explain the jet stream and its importance in detail. Also what makes California interesting and plays into this Mediterranean climate is not only the location of California to the jet stream, but then the presence of the cold ocean water. And specifically the idea that it's cold water with the Pacific, and it's not warm water. That also plays into this kind of milder climate that we have. You also get large temperature gradients in the winter due to the circumpolar vortex in California. You get the largest amount of rainfall on the windward side of mountains due to orographic lifting. You get the lowest amounts in the desert. You get the presence of warm light air over the coastal marine layer in stable air masses, and that's going to lead to drought. So all of these things, which are much more complicated climatic parameters, lead to this Mediterranean climate that we deal with. Now, what's really important in understanding how this all plays in climate is that it's not just one thing. And California has this look and this appeal because of all these different pieces coming together in the climate to present this picture that we're looking at. The idea that that in the winter it could be warm, it could be cold, it could be rainy, it could be not. Because we have topography, the idea that you're going to get areas that get a lot of rain and then other areas that don't. So we end up with something that looks like the Sierra Nevada mountains, but then on the other side of it, you got Death Valley and you got Mojave and you got this huge desert area because all the rain and everything ended up in this one spot because of the mountains. And then all of a sudden you get something completely different on the other side. And the idea that the reason why we don't get rain all the time or get lots of rain is because of the air, just the way that the air works in the world. It's very interesting when you really understand this stuff to be able to kind of put it all together and see how the sauce gets made, so to speak. And so here's kind of a breakdown of a different look at California. So if we kind of break it down into climatic zones instead of those bioregions, when people talk about California having a Mediterranean climate, we see that in the Central Valley, the Central Coast sees that, the South Coast sees that, but really the North Coast, they get this more of a marine west climate. You've got this highlands climate, and then you got the subtropical desert climate. And so what does that mean? Well, so for our Mediterranean climate, where we find ourselves here in Bakersfield, you can expect about 10 to 29 inches of range. Your characteristic vegetation is chaparral. Now, if you say to yourself, well, in Bakersfield there's no chaparral, sure. But also remember, that's because everything here has been settled and turned into agriculture. What would this area look like if it wasn't agriculture? And I would guess that you'd be into grasslands and chaparral shrublands for the most part. The marine west coast, so the north coast area, the Arcata, Eureka, all that stuff north of San Francisco, greater than 29 inches of rain. Redwood trees, Douglas fir trees, laurels, lots of different trees. And you say to yourself, oh, well, what's the difference? That rain and the consistent amount of rain, that becomes the difference between trees and shrubs and grass, right? So subtropical desert, dry grassland, scrubland, desert vegetation less than 10 inches. So why do we have it mostly grass or, not a lot of stuff growing here? Why do we get, shrubs and grass growing here? And why do we get trees here? And then this highlands area, I know it's not on there, but you're going to get trees growing there because you get it's different because you don't get rain so much as you get snowfall. And so it's differently impacted. These are basically, if you took all the mountain ranges, that's what we're looking at here. Sierra Nevadas, the transverse mountains, some of the coast range. What you're looking at is places with higher altitude where instead of this rain of the marine west zone, you're getting snowfall. And so from that snowfall, we get trees and we get shrubs. Here we get trees and we get shrubs. Here we get shrubs and grass, and here we just get grass. And it has a lot to do with this climatic amount of rainfall, the mean annual precipitation, not the idea of just like, did it rain yesterday or today? And so orographic lifting. Hey, look at this. Put myself in this nice blue box so you can see me pretty easy. In terms of orographic lifting, so Pacific storms bring precipitation, whether it's rain or snow, doesn't really matter, it's the same stuff, to California during the winter. Because of California's geography, moisture flows inland from the Pacific Ocean, condenses, and when we say condenses, squeezes together and becomes denser, right? and then rises up the west flank of the Sierra Nevadas. The orographic lifting, which is the cooling of the air as it lifts, causes clouds to form as the moisture cools, and the precipitation in the form of rain or snow is the result. So California's water resources primarily originate in the Sierra Nevadas and other Northern California mountain ranges because as the winter snow melts in the Sierra Nevadas, because it's also a high point for pretty much all of the state, and because we are west of the Continental Divide, for those of you who don't understand what that means, is that the Rocky Mountains are the Continental Divide. So everything west of the Rocky Mountains flows downhill to the Pacific Ocean. Everything that's east of the Rocky Mountains flows downhill either to the Atlantic or to the Gulf of Mexico. And so even though the Sierra Nevadas are a high point for California, everything is still flowing downhill to the Pacific Ocean. Now, because of the orographic lifting, because of the topography and everything going up to the mountains, that's where the rain hits the most, or the snow. And then once that stuff decides to melt or decides to work its way through the groundwater, it starts trickling all the way down to the rest of California, down and out to the Pacific Ocean. That's how we start getting things like the Kern River to form. We get that moisture to drop. Rivers flow out into lakes or out into the ocean. They evaporate into a gas, and that's the whole water cycle going through California. The east side of the Sierra Nevadas then is in a rain shadow, because what happens is that all that moisture gets dumped at the Sierras, and then once that, because we've forced that pressure has forced the air up. Once it gets up there, and then the mountains disappear, it doesn't have that pressure forcing it to go dense again. So what happens is the pressure drops, but what happens with the pressure drops is there's not that pressure that formed the clouds. Remember, it cooled as it went up and condensed into clouds, and then once it got high enough and got enough pressure, the clouds then bursted and rained or snowed. Well, now there's no pressure forcing it up, so it comes down. But what happens is that air pressure comes down, and it comes down as air and wind, but no more rain, no more snow. So that other side becomes a rain shadow, and that's why the eastern part of California is desert. So here's another look at what I was just describing. So hopefully with pictures makes it a little bit easier. But from the ocean, we get moist, warm air blowing onshore. As the air rises over the mountains, it cools, condenses, causes moisture to fall as precipitation. But then on the leeward side, so not the windward side, but the leeward side, the dry air descends, becomes warmer, promotes evaporation. We get none of this precipitation stuff. We get none of that condensing. You just get hot, warm air and desert. And so here is a look. Now we're looking westward towards the Pacific Ocean from the southeastern desert. So the snow-capped mountains in the background, those are the Sierras, and then we've got our southeastern desert over here. But you can see there's just a point where we get snow, we get snow, we get snow, and then we lose that topography, that push, and then all of a sudden we don't get any of that anymore. And this down here at the bottom, this diagram shows we get the cool, moist air coming over from the Pacific. It goes to the coast ranges, which pushes it up. We do get rain happening here in the coast ranges as well. And then guess what? We actually have a little bit of a rain shadow here in the Central Valley as well. We don't get as much rain as you do if you lived in Santa Barbara or Ventura or Monterey, Santa Cruz. Don't get anywhere near as much rain here in the Central Valley. But then we get a real big push because we go from this real low valley to the real high peaks of the Sierra. So we get a lot of push. So we get a lot more rain, which actually ends up snow most of the time can get those big dumps of snow in the Sierra, and then because of that real huge loss of topography, you get a real big rain shadow effect here in the desert, to where you get nothing. You hardly get any precipitation at all. So that's why we don't really talk as much about the rain shadow effect here, because we still do get rain in the Central Valley. We just don't get anywhere near what we would get on the coast ranges or up in the Sierras. But if you compare the Sierra with the desert as opposed to comparing the coast with the Central, there's much more of a rain shadow effect, much more noticeable of a rain shadow effect here, because you don't get any of that precipitation, whereas we still get some precipitation in the Central Valley. And here's just an example. So in the Sierra Nevada, this is Yosemite. You can see lots of big green conifers, lots of big trees that need lots of precipitation, whether that's via snow or rain. Just the idea, if you're going to have trees and rather large trees growing and trees all over the place, you're going to need vegetation. Whereas you can see the type of trees that grow out in the Great Basin forest, and you can also see the soils that they're dealing with out in the Great Basin, which is that area just past the Sierra Nevadas on the eastern side. Our deserts are part of the Great Basin. So you can get trees out there, you can get some vegetation, but it's going to look much different than the areas that get a lot of precipitation. Slide myself over here. In terms of temperature, so what are our kind of climatic temperature trends for California? So in the winter, coastal Northern California, so the North Coast area, we're talking about 48 degrees. South Coast area, 57. Southeastern deserts, 54. Mountain temperatures, you get freezing at 5,000 feet in Northern California and 7,200 feet in Southern California. The Central Valley, if we get an inversion layer, we can range from 27 to 46. So we get that kind of variable winter temperature. But that was one of those things we mentioned earlier when we were talking about what makes it Mediterranean climate for California. In the summer, because of the coastal marine layer and the wind transports marine air inland. So basically, whatever's happening over the ocean in the summers, that same effect gets felt 62 miles inland. And so that's why the summers here are pretty nice usually. So coastal areas, you'll get like 57 to 61. South of Point Conception, 64 to 72. Central Valley, 75 to 82. Now, I know if you're sitting there going, what are you talking about? 82 degrees. It's always like 100. But remember, we're talking about all summer long. So not just the stuff at the end of summer when it's really hot, but also that stuff at the beginning of summer. And we're also talking about temperature all day long, right? Because it's the average temperature. Deserts beyond the marine air penetration, 79 to 85. Death Valley averages about 100. The mountains, 68 to 75 at 5,000 feet and 57 to 64 at 8,000 feet. Do I expect you to memorize all of these different temperatures? No. It's just the idea of just to kind of get an idea of why we talk about the different bioregions and this idea that even though California, we think about it as one entity, as one state, it's really a lot of different areas that are affected in different ways. If we look at this graphic here of the regional temperature trends from 1895 to 2017, we can see the kind of the different temperatures that we have in these areas, but more importantly, the different changes in temperature. So in terms of minimum temperatures, average temperatures, and maximum temperatures, the increase that we've seen in that over 100-year period. And you can see in some areas, what's really interesting is that there is a definite increase in a lot of these places in their minimum temperatures. So their average temperatures are definitely going up. The the maximum temperatures are still increasing as well, but definitely a large increase for a lot of these places in their minimum temperatures, which tells you that everything's getting hotter. Because if your minimum temperature is going up, then your average temperature is always going up. Maybe your maximum temperature is not increasing all that much, right? So maybe, you know, if the hottest it's been in Bakersfield is 112, you know, maybe it's only now it's 113 or something. But it used to maybe cool down to, you know, like, oh, well, you know, there's some days where it was like 20 degrees. Now it's, well, there's the lowest it's ever been lately is 26 degrees, right? But that's a big shift. You know, everything's getting hotter. And it's not a good sign. It's something that we'd like to, if we're going to keep this Mediterranean climate or overall Mediterranean climate, it's something to really consider when we're looking at the temperature increasing in all of these areas. Slide myself out of the way. So kind of looking at the same thing. So this is an 11-year running average in terms of California summers. So the temperature departure from 70.4 degrees, which was our average. So over the last, over these times. So if we kind of consider 70 degrees to be a good average temperature, we were 3 degrees higher than that in 2017. And you can kind of see this general trend right here lately of the idea that we're not really getting below that at all. It's always getting above, right? So if we look at that 70.4 degree average, you see all these blue lines over here. So these are all the times it was below average, was all these blue ones. And it's way below average in the early 1900s, way below average in the 20s, way below average in the 40s and the 60s. But, you know, then there's times where it's above average, and it's a little bit above average, and it's above average. But now look at lately. Look at the 80s, the 90s, the 2000s, the 2010s. Where are those times where it's below average? It's okay if it goes up and it goes down and it goes up and it goes down. Then we're like, you know, it is what it is. But now it's just going up. And that's not, that can't be good. That, you know, look at all this blue over here. And then look at over here. Where's all the blue? It's only going up in this time. So, you know, climate change is a thing. And, it's, you know, as fire ecologists, it's something that really we've got to bring our attention to, and we've got to really try and understand and educate people about, so that they understand that it is a thing, and this is how you can see it, and this is what will happen with that expected change. So this graphic here, I don't know if there's a good place to move myself out of the way. I guess I'll go right here. So mean temperature patterns in California over a 10-year span, so from 1992 to 2001. And this is occurrences of a temperature equal to 100 degrees for 3 consecutive days. So you can see, so for July, August, and September, so you can see that in the southeastern desert area, we get a lot of occurrences. Now, to me, what's interesting about this is September 15th. So to me, I'm thinking, you know, fall time is September 15th. But we're still getting, in some areas, 6 to 8, 3 to 5 occurrences of over 100 degrees on September 15th. And to me, what this sort of graphic is really indicative of is the idea of this extending of fire season. So when we talk about fire season, we usually think about the summer. You know, people go and fight fires for the summer. But wait a minute, if you're a firefighter, you know, how are you going to come and take classes here and fight fires if on August 15th we're still having 9 to 10 times where it's over 100 degrees in the southeastern deserts, and in the Central Valley we're having 6 to 8 or 3 to 5 of these. We're having lots of these periods where the temperature is really hot and really conducive for fire. And then even in September, we're still having periods where the temperature is really conducive for fire. That means that, our fire season is longer. And if it starts happening, which it's happened as well, that summer starts happening quicker on the other end, and we're now all of a sudden we're talking May to October. That's a long fire season. And so I used this graphic earlier, but I'm coming back to it because we didn't really have to talk about it before. But the idea that California is getting hotter. So here's the historical look at it. So from 81 to 2010, there's our average degrees of cooling needed each day. Lots of cooling needed, of course, in the southeastern deserts and in the Central Valley. Now, if we look at the idea of how much cooling are we going to need, how much are you going to have to crank the air conditioner in the future? In 2080 to 2099, it's looking like everything looks like it does in the southeastern desert. Now, if that's the case, if this is what the temperature is going to be like, what do you think the vegetation looks like here? Do you think it still looks the same? Do you think it still looks the Sierra Nevadas and Sacramento and the Bay Area and LA and all these places? Do you think it still looks the same vegetationally if this is the weather pattern? Or, sorry, the climatic pattern. Because my guess is it won't. It'll change. And it'll change completely. And fire will be a big part of that. And so this, let me move myself down here out of the way. This is something I was kind of alluding to before. So in the early 1970s, wildfire season was 5 months long. Now we're talking about 7+ months long. Average number of large wildfires per year in the 80s, 140, in the 90s, 160. In the 12 years of the 2000s, around 250 large fires. So we've got temperatures that are rising, we got snow melting sooner, and we got forests that are drier for longer and have more fuel in them. It's not a good combination. It's a good combination if we want fire, but the thing is we want fire that we can control. Good fires that are manageable, that we can use to clean up understory, not big, huge mega fires that burn the whole forest to the ground. So let's talk about precipitation then. Move myself into a nice opening here. So with precipitation, the mean of the jet stream goes through Northern California. So storms increase as they move farther down the state, which works out well for us. That's why you're going to get much bigger storms in Northern California. That's why it rains a ton in Humboldt and San Francisco and these places, but we don't get as much happening down here, not to mention the whole orographic lifting process. Most of the precipitation comes farther out from the cold front, and so gave you this graphic right here so you can see this is the front. So this is the cold air moving its way. Over here we've got the warm air that's getting pushed up, and as the warm air gets pushed up by this cold air, then we get our creation of our clouds, we get our storm, but then our rain is actually happening way out here in front of the front. You will get some rain along with the front, but you also get rain happening farther out from the cold front. That rain, like we talked about, usually gets deposited at the high terrain, and so the greatest precipitation in California happens in the mountains. And once again, that's due to that orographic lifting process. And so looking at it again, the effect of topography on average annual precipitation. So the coast ranges to the Central Valley, to the Sierra Nevada, to our rain shadow desert. So if we look at precipitation in inches, coast rain, so at the coast we get some rain, but we definitely get more in the Coast Range Mountains. As we get into like Silicon Valley area, we get a little bit less rain because of that whole minor rain shadow effect. We hit another part of the coast mountains, and we get some rain, but it's not as high. You know, a lot of this is foothills, so you don't get as much rain. And then we get into the Central Valley, and we don't get a lot of rain at all because we've already dumped rain here, dumped some rain here. So we get rain, but not a whole lot of rain. But then we get that orographic lifting process happening again and get it to really build up because we got really high topography. So we get a lot of orographic lifting. It's got that air mass has to push hard and condense a bunch to get over those mountains. And so with doing that, get a lot of rain happening here. A lot of rain happening on this west side of the Sierra Nevada mountains, but then nothing on the other side. And you can see where we are here in the Central Valley compared to the deserts. It's not that big of a difference, but it's enough that we can get some grass and get some shrubs, whereas they get a lot less happening on that side. Slide myself over here to the right. So then also looking at it from the idea of precipitation going into the groundwater flow, as well as this whole kind of water cycle process to it. So you get the wind, the prevailing winds, the jet stream blowing those westerly winds. So when we say westerly wind, whenever you say a wind in a direction, it's the direction that it comes from, not the direction it's going. So if we're talking about westerly winds, that's winds coming from the west. So we get those westerly winds blowing in from the ocean. Okay, they then create a moisture-rich air mass. It's going to rise over the coastal mountains, cools and precipitates. Condensation and precipitation occur, so we get some moisture there. We'll get some groundwater flow that'll, go back downhill. We do get some coming into our area as well, even though, wait a minute, Dr. Roy, you said it's all downhill to the Pacific Ocean. Yeah, from the highest point in the Sierra Nevadas, but when it comes here, just because it comes this way doesn't mean it's not going to come down this way and go out, or go that way and go out. It's still going to work its way downhill, but downhill might go this way and then go that way. But what also happens is if we get, because of the heat that we get, because we're down lower in the valley, we get more evaporation and transpiration, and that stuff starts heading off. But we do also get some groundwater recharge here. But then we get these huge masses built up because of orographic lifting over the Sierra Nevadas. And so we get lots more condensation, precipitation, get lots of stream runoffs. That's why our big streams like the Kern River come from the Sierra Nevada mountains. And then the sinking air warms, becomes relatively drier. We don't get anything happening here, but you still do have, you get some groundwater flow, you get evaporation happening, and so then you get these dry lake beds, or you get the salt flats that you get in some of the Great Basin, because you don't get that rain. You don't get any of this that you get in these other parts of California. So then, slide myself over. Yeah, or how about this? Boom, playing in the snow. Snowfall. Okay, so another way that soil water, or the idea that having moist, fertile soil happens, is that we get the replenishment of soil water through winter until March or April. The snowpack will melt and provide moisture throughout the summer for a lot of places, and that's just kind of normal, and what we kind of plan on, because we know that with what we've talked about with the Mediterranean climate before, that summer brings drought and doesn't bring precipitation events. So we need to get enough precipitation and enough snow during the winter, that then when that stuff melts off, that's how we get our water during the summer. There is this linear relationship between altitude and average frozen annual precipitation. So higher you go, more snow you get, as opposed to rainfall. Slide myself out of the way. But where's the effect of climate change, and what are these things that should be concerning to us, or kind of open our eyes to the problem? So we have dwindling snowpacks in the Sierras. And so you can see how it kind of breaks it down into different versions of the Sierras. Of course, here we are in Bakersfield, so we're getting kind of the southernmost portion of what they consider the southwest portion of the Sierras. And so historical averages. So these are the elevations of the center of the snowpack. So if this is our snowpack, they're saying that's the center of the snowpack, right? And so we can see where those heights are. And you can see down here in the southeast, it's really a lot higher than it is in the northwest. Even though you might not be used to meters, I'm pretty sure you can tell that 3,000 is much higher than 2,000. So that means that, let's say this is the 2,000 up in the northeast. That means the center of the mass is way up here in the southwestern part. And then with 1 degree of warming, 1 degree Celsius of warming, increases the chances that the slope will shift, that it'll shift upslope. In that northwest, it's really big. If you get a temperature change up here, we're a little more used to it down here, so not as much, but 33% is still, that's pretty good. That's a third of a chance, right? Whereas 70% and 50%, that means more than likely it's going to happen that you're going to get a big shift, which means there'll be less snowpack. And so when you look at this winter warming and the increased chance of below average snowpack and the snowpack shifting upslope, very good chances of those things happening as it warms, right? And so snowpacks, why does it matter? Well, key for our natural resources, salmon runs, the giant sequoias, the recreation people enjoy, plus the idea, and I think really the more important thing for all of California is that Sierra snowmelt provides 60% of Southern California's water and resources and 75% of the state's agricultural water. And then, not to mention, on top of it, the wildfire risk by having areas that are just drier with less available water. And so that becomes really problematic. Some interesting things that happen in California. So the North American monsoon, that comes through July to early September. So every once in a while, even though we have these summer drought areas, we can possibly get some moisture happening. But you can see with California and with us kind of in Bakersfield over here, not everywhere in California is going to get this experience of the North American monsoon. And really, it just it affects Southern California and the southeastern deserts a little bit. You can get the occasional thunderstorms and lightning. So you can actually, our desert areas can actually get some rainfall and some actual moisture once in a while. And so you'll hear every once in a while about like huge desert blooms or things like that happening, because it's not that the southeastern deserts don't have vegetation. They have plenty of vegetation. They just don't have the moisture to keep that vegetation alive and keep it growing. So if you hear about like some super bloom happening out in the desert, more than likely there was some sort of event, moisture event that happened, and the North American monsoon is a lot responsible for summer events happening in those southeastern desert areas. Lightning. Lightning is an important climatic event, important weather event, but we're going to look at the climatic pattern for California because it's one of our two ways that fires can get started. So in 1985, BLM, the Bureau of Land Management, installed a system to measure cloud to ground strikes in the Western U.S. And why is that important? Because that's how we started tracking lightning and really starting to figure out patterns and look at lightning in terms of not just being a weather phenomenon, but trying to look at the climatic idea of lightning. Where do we get the highest amounts of lightning? get it in the mountain ranges. So the peninsular ranges in SoCal and the Sierra Nevada mountains, and then also in the deserts as well. But success of ignitions depends on whether they strike flammable targets and then whether the weather conditions exist for fire spread. So not all of the time are you going to get lightning strikes. What's interesting is there's when the BLM did their measurements from 85 to 2000, there were over 1 million lightning strikes in California. So if you just kind of do the math in your head and say, well, how many fires do we have a year and how many lightning strikes were there, you can see there's a bunch of lightning strikes that didn't do much. But that's also because half of the lightning strikes happen in the desert region where there's not that much to burn. So that is at least helpful in that way to avoid a lot of fires. The most prevalent lightning happens in July and August, which happens to coincide with a lot of the drier periods across the state, which means, at times when we can expect a lot of fires to happen. And then from noon to 4 p.m., so also during the heat of the day. What's also interesting, at least recently, was the huge lightning storms that we had this past year, which all of a sudden, you had a lightning storm event that was uncommon in Northern California, where all of a sudden we had fires left and right and huge complexes and millions of acres lost because of one of these big lightning events and having those right weather conditions and a lot of flammable targets. Slide myself off to the right here. So this kind of gives you, lets you kind of see where are areas where you get a lot of lightning. So you'll see on the east side of the Sierras, and then the southeastern deserts is where we have our biggest spots for lightning strike density. And you can see definitely that whole southeastern region is pretty lightning strike heavy for the most part when you compare it to other places. But really it's definitely on the Sierras and then on the east side. And then you can see when do we get the most, and you can see that July, August is that time where you see the most strikes happening. So then another climatic variable that we wanted to look at, potential evaporation and runoff. So what we're talking about here is the idea of the accumulated soil waters from the winter storms starts getting pumped out by vegetation through transpiration. So when we say transpiration, that's the water that gets used by the plant so that it can grow and that it can survive, and then it transpirates into the atmosphere and then cycles back. Potential evapotranspiration, that is defined as moisture returned to the atmosphere from evaporation from wet surfaces and the transpiration that we just talked about from plants. And potential evaporation is when you assume no water control. So, you don't worry about dams and other things that might affect the amount of water that comes through. So, evapotranspiration is definitely a function of temperature, also wind speed and relative humidity. And you get areas with cold summers, like the Sierra Nevada and Pacific Coast. You get 30 to 39 inches. Areas with increased temperatures, 30 to 59 inches in Central Valley and Inland SoCal, and 50 to 98 inches in southeastern desert. And so you can see that the different areas have a different effect in terms of evapotranspiration, and a really huge effect when it gets to the southeastern deserts. And then a lot of these places, the precipitation the potential evapotranspiration exceeds precipitation in the summers, and that's what leads to our drought that we're used to. The average annual precipitation is greater than evapotranspiration. The only only the northwest coast and the northern Sierra Nevada avoid the problems associated with summer drought and evapotranspiration. You do see surpluses of this precipitation in elevations above 5,000 feet because you get snow, and the runoff is less than 4 inches over the rest of the state. And so how does that play into fire ecology, or into why should you care about evapotranspiration? So this chart, so we're looking at years relative to a fire. So before a fire, we can see that our evapotranspiration is higher. Then we have our fire, and we don't have much evapotranspiration happening because there's not anything there to basically transpirate the water. But as we start, as our forest starts growing again, we see that we'll have low severity fires. So if we do have fires, it won't be that bad if we have these higher evapotranspiration rates closer to what we see in the forest, whereas we can expect high severity wildfire with lower evapotranspiration rates. Now, if you're sitting there saying, well, isn't that kind of counterintuitive? Like, if there's more evapotranspiration happening, shouldn't that be worse? Things will be drier and kind of more problematic. And yeah, I can see that, and I understand that as well. But you also have to think about it. It's evaporation and transpiration. So to me, when I look at this and I think about the transpiration part, in order to have high amounts of transpiration, you have to have lots of plants, or you have to have big plants, or you have to have lots of big plants. And so the idea that you have more evapotranspiration, you have more plants, you have more green things, and green things don't burn as well as brown things. And so to me, it's more the idea that you've got more plants, that you're getting farther away from the fire, and so you can get more evapotranspiration. And so you can actually, it's, to me, when I look at this and think it might be counterintuitive, I think about the idea of plants. In terms of, this is groundwater recharge. So when we look at 1981 to 2010, and look at the idea of groundwater recharge, and we can see areas where we get lots of groundwater recharge and areas where we don't get as much groundwater recharge. Now, when we look at this same chart lately, it's a lot different. Where's all of this? You know, where the color pattern has changed, right? We're not seeing these darker colors much anymore. We are seeing it in a different area. So, I mean, that's nice for this area right here, but what about the rest of it? And so it's something to really take notice of, is kind of these changes that are happening, and these changes in terms of our climate that affect all these different parts, right? It's not just the idea that it's getting hotter, but that our groundwater is being affected, our evapotranspiration is being affected, our the type of weather patterns that we'll see are going to get affected. And then also our plant phenology and its effect on the fire season. So fire season usually begins in early summer in most parts of California, or really the idea is within 2 months of the last winter storms. That's when our growth flushes have finished. And so then the fire hazard begins once the moisture of the winter is kind of depleted or worn off. So that's usually June, July. And so when we talk about phenology, we're talking about the cyclic patterns. And so it's going to depend on seasonal temperature and precipitation cycles. It's going to vary with altitude. But at our lower elevations, so our grasslands, the growth flush begins with the first winter rains, peaks in spring. At our higher elevations, where we get shrublands and forests, precipitation is heavier, soil water's used more, so because you got deeper rooting. Your growth flushes are in late spring after the temperature warms. The shrubs are in between, right? Because if we got the grasses in spring, we've got the shrublands and forest in late spring, maybe early summer, and the shrubs come somewhere in between there. Whereas the high mountain evergreen forest, the growth flush happens after snow melt in early summer. And so when we start thinking about fire season and when do we have to start worrying about fire risk with these places, if we really understand our climate patterns and really understand and start looking at the storms and when did the storms end, okay, so then now we can kind of figure out when the moisture is going to be gone, and that's when we have to start worrying about the fuel being available for the fire. And so we can kind of do that, separated out by elevation in terms of plant phenology. In terms of climatic variability and fire history, there's this energy upgrade site. You can pause the video here and take a look at that. It's where I got this picture from, and it'll kind of show you the difference between what exists and what can be expected into the future. But what's interesting in looking at this is this increase in area burned. It's really the worry about how much more these fires can do and where we could see these big fires happening. In terms of climate change, climate variability and fire history, climate change is really important in fire ecology because the variability in temperature and precipitation at scales of years and decades will then influence the regional vegetational productivity, fuel moisture, and fire occurrence. And so these climate trends are important to us because they'll tell us what we're going to look at in terms of vegetation, in terms of fuel moisture, in terms of fire occurrence into the future. We're really concerned with that precipitation variability, which I've talked about before, because that just it's really obvious. The deserts get very little rain, very little growing there. Central Valley gets a little bit more rain than that, so we get stuff that's a little bit bigger. The Sierra Nevadas and the other mountains, they get a lot of rain and snowfall, so there we got big trees and we've got lots of shrubs and lots of fuels. So it's really important for us to understand precipitational variability. It's also important for us to really understand that drought effect, because if we're really comfortable with the idea of how drought happens and why it happens, then we're really comfortable with the idea that our live fuel moistures for those fine woody fuels, those 1 hour fuels, are going to be really important to pay attention to when fire season comes around, because that's the stuff that's going to dry up the quickest. That's the stuff that's going to tell us, could this be a really problematic day for fire? The relationship with fire history is dependent on fuel buildup in the ecosystem mosaics. So when we look at these mega fires, one of the big reasons we can be worried about that is because it's not a big deal to have fire in California. The climate is suitable for fire. Everything is set up to use fire. We don't get that decomposition, so we need fire to clean things up. So fire is going to happen. Fire is going to clean things up. But do we want it to wipe everything out, or do we prefer this ecosystem mosaic look? Because I think we're all very happy with that ecosystem mosaic look, but don't want these huge mega fire burnt out areas. And so this picture here, the reason I put this in, this is in the Sierra Nevadas, in Yosemite, is to really kind of start kind of training your eye as much as I can, to really help you out. Move myself off that mountain. To start seeing things and looking at pictures and trying to understand what's happening. So when you look at these trees, look at what's on the ground. See all the snow on the ground? So we know snow is moisture, plenty of moisture here. But wait a minute. Dead tops of trees. Dead trees, dead trees, dead trees. Wait a minute. Why are there a bunch of dead trees if there's a bunch of moisture on the ground? So something else is happening here. So there's some other problem happening in this area, because these trees should be fine. this tree should look like that tree, but it doesn't. It's dead. That's dead. That's dead. That's dead. That's dead. That's dead. And that starts telling us that something else is happening here. So if we understand how to look for some of these patterns, if we understand these patterns, understand what it means to have moisture on the ground, then we can start looking for the other patterns that help tell us if there's a problem going on or if there's something else that we need to pay attention to.